Welcome. Tonight we're going to discuss performance optimization, how to make queries go faster and also allow concurrent access by multiple users. We'll discuss query optimization, transaction schedules. That's how the database management system prevents conflicting queries from running concurrently. And finally, indexing. The goal of database performance is to execute queries as fast as possible. A database performance tuning is a set of activities and procedures that reduce response time of the database system. Fine-tuning the performance of a system requires that all factors must operate with minimal bottlenecks. So we've got a system comprised of many components: a CPU, a RAM, hard disk, network, operating system, and an application. And we want to tune all of those, and it'll all be part of the query processing that we do. And this is the flowchart for query processing. So we can see that we're going to have a query. We'll use a parser and translator to take the query, put it into a relational algebra expression. The query optimizer will then get statistics about the data and form an execution plan. This is the best execution plan that it could come up with in a limited amount of time with the statistics it has available. So it's always possible that you can fine-tune that execution plan to improve performance. Then the evaluation engine gets the data that's requested from the query and sends it back as output. So client side, we've got performance tuning. So SQL performance tuning generates a SQL query that returns the correct answer in the least amount of time. And it uses a minimal amount of resources at the server level. Server side performance tuning, the DBMS environment is configured to respond to clients' requests as fast as possible. And again, optimize the use of existing resources. Parsing is where the database management system parses the SQL query and chooses the most efficient access or execution plan. Execution, the database management system executes the SQL query using the chosen execution plan, and fetching the DBMS fetches the data and sends the result set back to the client. So a query is broken down into smaller units. The original SQL query is transformed into slightly different version of the original SQL code, which is fully equivalent and probably more efficient, at least as efficient. The query optimizer analyzes the SQL query and finds the most efficient way to access the data, and it has an access plan, the database management system specific, and it translates the client's SQL query into a series of complex input-output operations. All the data in a database is stored in data files. Data files automatically expand in predefined increments known as extends. The data files are grouped in file groups or table spaces. A table space is a logical grouping of several data files that store data with similar characteristics. You also have a data cache, and that is a shared reserved memory area. The database management system stores the most recently accessed data blocks in RAM. The SQL You also have a SQL cache or procedure cache, and that stores the most recently executed SQL statements or stored procedures. The database management system will retrieve data from permanent storage on your disk and places that in RAM. An input-output request is a low-level data access operation that reads or writes data to or from computer disks. A data cache is faster than working with data files on disks. Majority of performance tuning activities focuses on minimizing these input-output operations with disk. A relational algebra expression may have many equivalent values or expressions. So for example, we could take the one relational algebra expression, select salary less than 75,000 from where we project salary from the instructor table. So that might be more efficient than doing it in the reverse, which would give us the same answer. So equivalent to that query is where we project the salary from the results that we get from selecting the rows that have a salary less than 75,000 from instructor. So some equivalent relational algebra expressions will, on the face of them, be faster. If we first reduce the data set to just the salary field and then filter the 75,000, we have less data to wade through, and we can presume it might be faster. The query optimizer uses logic like this to assist in query performance. And we talked about evaluation plans, but it's an annotated expression specifying a detailed evaluation strategy. It can use an index, and we'll talk about those later in this lecture, to help improve performance, or a complete relational scan. Algorithms that are used for query optimization are based on selection of the optimum order to achieve the fastest execution time and selection of sites to be accessed to minimize communication cost. And they're evaluated on the basis of timing of the optimization, automatic query optimization, manual query optimization, static query optimization, and they take place at compilation time. And that is a dynamic query optimization. So the cost that we use in our optimization function is going to be overall the elapsed time for answering a query, and it's going to include the disk access time, CPU time, and even network communication time. Although the models in the book are for the most part focused on disk access time. So statistically based query optimizing algorithms use statistics that are stored by the DBMS to determine the best access strategy. You can generate this statistical information, or we don't, the DBMS does, either through a dynamic statistical generation mode or a manual mode. In the manual mode, we have a rule-based query optimization algorithm based on a set of user-defined rules to determine the best query access strategy. And in terms of disk, the type of statistics we'll need are the number of seeks it might take to get to answer our query. And a seek is where you're moving the disk arm to the proper location on disk. And then block transfer is going to be, once you've got it on the right place on disk, you're going to be reading the information from that disk, and how long does it take to transmit that information. So some of the sample measures we might have for different types of database objects. For a table, some of the statistics are the number of rows, the number of disk blocks for the table, the row length, the number of columns in each row, the number of distinct values in each column, a maximum value in each column, minimum value, and which columns have indexes. And an index can help improve performance. So what we're left with ultimately for deciding which execution plan is best is an optimization problem. We want to minimize the query cost, and in this particular case, the book narrows it just to disk seek and disk transfer. And the objective function, as we see here, is the cost for B blocks plus S seeks. So B times the transfer time it takes to transfer those blocks once we found them. And then the seek time times the number of seeks we have to do on disk. And we also have constraints in terms of the amount of time we can spend on making a plan. We don't want to spend hours optimizing a query that only takes milliseconds to run. So again, as I mentioned a few minutes ago, there's always room for improving these execution plans. So we can have a delay in the processing of an input-output operation that slows the system. And these delays can be caused by a CPU being pegged. In other words, something on the system is taking all the CPU time. Amount of available memory is totally used, and we have none available for expanding cache. The hard disk is extremely busy, and so we cannot get data from the disk in the time we normally would take. The network is congested if we're going to a server that's on another node on our local area network, or the application code may be inefficient. Okay, so that's some background on query optimization. One of the other tasks done by a database management system in terms of performance improvement is running of multiple transactions. Multiple transactions can run concurrently, or in other words, simultaneously. And if we do it right, they can run well, and they can help we can help the database management system coordinate them so they do not cause problems with each other. And a guy named Jim Gray did some seminal work in this area. He was awarded the Turing Award for that. He worked at Microsoft, and we're going to be looking at what he did. The book, of course, includes it. It's critical in terms of understanding transaction schedules. So it's in the chapter 17 in our book, and we'll take a look at it here. So A few weeks ago, we looked at the case of what a single transaction running alone, what it does. Let's review it, what goes on. A transaction is a logical unit of work that must be entirely completed or aborted. It consists of either a select statement, a series of related update statements, a series of insert statements, or some combination of select, update, and insert statements. And we cannot allow the transaction to fail. In other words, every one of those update and insert statements must be completed to leave the database in a consistent state. If we don't, then the database will be in an inconsistent state and we have to do a rollback. So a consistent database state is all the data integrity constraints are satisfied. We begin with the database in a known consistent state, and then we leave it in a consistent state. Transaction is formed by 2 or more database requests. Things like an update to a record to remove $50, and then an update to another record to add $50 to complete a transaction. They both have to be completed. So they look at the series of statements as a single SQL unit of work in an application program or in a transaction. So an improper or incomplete transaction can have a devastating effect on database integrity. Here's how it works. So we have applications that use the database. They will write every result from every single individual SQL statement into a transaction log. Then at the end of the transaction, if everything went okay, they write a commit. So it's in our transaction log. It has a begin transaction, and then it has a commit. Once you've got the database management system reading the transaction log, and as it reads through and it sees a commit, it'll take that series of transactions and move them into the database. If it doesn't find a commit, or if it finds an abort, then it will not move the information into the transaction, from the transaction log into the database, thereby leaving our database in the consistent state it was, and we don't pollute it with an incomplete transaction. So the classic example of the need for transactions is we're going to move money from one account to another. So we're going to move it from person A's account to person B's. So the actions we have to go through are read person A's balance, subtract $50 from that balance, and then we write that new balance into person A's account. Next, we read person B's balance, we add $50 to person B's balance, and then we write that. So the issues we have to deal with, if there's some sort of failure, system crash, hardware failure, some kind of failure, and we've only taken $50 out of person A's account, and we leave it at that, and we start up, and then we go on our merry way, then person B is going to be very angry because they never got their money, and person A will eventually be angry because they still owe person B $50 and they lost $50. So that's if we're even if we're just a single transaction. Imagine if you have multiple concurrent transactions going on at the same time. That's what we're going to look at for the remainder of our discussion of transactions in this lecture. Multiple concurrent transactions and how to prevent them from causing an inconsistent state in the database by stepping on each other's work. So we have this concept of atomicity. All operations of a transaction must be completed. So if we have two update statements or two write statements like we did, like we see up above, write A and write B, all these must be completed successfully or the whole thing's aborted and we don't update the database at all. Consistency is that we can leave the database in a consistent state even after all of the multiple potentially conflicting transactions are working. Isolation, durability is that we, once the transactions are committed, they are permanent. They become permanent in the database. Isolation means that we don't want one transaction from one application to interfere and cause error in the operation of another transaction from a different application. And we're going to look at this concept of serializability, and that ensures that the transactions, the schedule of operations for concurrent execution of several different transactions yields consistent results. And again, you know, we have this consistency. Once a transaction is complete, the database is in a consistent state. So when we have multiple transactions being done simultaneously, the problem of transaction management becomes more complex. Isolation is the key. Don't let these multiple transactions that are running concurrently interfere with each other. Isolation can be ensured by running the transactions serially in the most trivial case. And what that means is we we only allow one transaction to run at a time. We run it, put everybody else on hold. When it's done, then we start another transaction and we run that. As you can imagine, executing multiple transactions together concurrently instead of serially has significant performance benefits. And so the query optimizer becomes involved, and it has algorithms to help it decide whether or not or which transactions it can run simultaneously or concurrently and not cause problems. So here's the different transaction states that we go through. Active is the initial state. The transaction stays in this state while it's executing. Partially committed, after the final statement in the transaction has been executed successfully, then it's partially committed. Failed is after the discovery that normal execution can no longer proceed. Aborted, after the transaction has been rolled back and the database is restored to its prior state. And finally, committed is it's put into permanent storage in the database after a successful completion. So with concurrent executions, we need to do a coordination of these simultaneous transaction executions in a multi-user database system. Our objective, ensure serializability of transactions in a multiple database environment. Some of the problems we can run into with concurrency are a lost update. It occurs when two concurrent transactions are running and some data element is updated, and one of the updates is lost. So in other words, let's say both transactions were working on the same data item. Transaction A added 50 bucks to the transaction, and then transaction B set the value to $10, overriding what transaction A had done. So we lost transaction A's update. Uncommitted data. When, again, two transactions are executed concurrently, the first transaction is rolled back after the second transaction has already accessed the uncommitted data. So we add $50 to account A, transaction B then reads account A, then they add $50 thinking that they now have 100 in there, but transaction A decides to roll back, and then you get a write back into the database with the wrong value. So you get a variety of these type of inconsistencies, even inconsistent retrievals. So there's some problems that we need to look out for. One of the common themes you'll notice is if both transactions we're looking at are doing some sort of update operation on the same object. So that's a clue, and that's actually going to be our rule, and we'll look at that shortly. So the scheduler in the database management system establishes the order in which operations like transactions are executed. It interleaves the execution of these database operations to ensure serializability and isolation of transactions. So what does that mean, serializability? Well, that means we're going to put two transactions together, and those things can be virtually swapped around so that they are in effect run serially, even though they're run concurrently. And we'll take a look at how we do that in just a moment, but that's what serializability means. We know that a transaction that is run after another transaction has completed cannot interfere with that transaction. And so the goal is we want to put transactions together that we can swap the various elements of the transaction around, and that if we can do that virtually, we're not going to actually do it, but if the query optimizer can virtually do it, then it knows that it can run those two transactions together and they will not interfere with each other. And that is where they end up with a serializable schedule. And this is the interleaved execution of transactions that yields the same results as if the transactions were run serially. And again, the guy who cooked this all up was Jim Gray at Microsoft, and he won the Turing Award for his work on this. And for those of you in computer science, that's the computer science equivalent to the Nobel Prize, since they don't have Nobels in computer science. So let's consider an example. Here's a serial set of transactions. One follows the other. They cannot conflict with each other. Let's consider a second example. Likewise here. They cannot interfere with each other because they are run serially. One completes before the other begins. Now here's where it gets interesting. Here's where we see a case where the two transactions interleaf with each other in time. But if we can virtually, in other words, we're not going to actually swap them, but if the query optimizer determines that it could swap them, and they could then be running serially. So it knows they won't interfere with each other. So if we can virtually swap one of the transaction and then portions of the other, and the result is a virtual serial schedule, then there won't be any conflict, even if they're running in an interleaved manner like this. the query optimizer does this work to see what transactions it can run together. It does not actually swap them to form serial transactions, but sees if it is possible to do so. If it is possible, then the two transactions can run concurrently. So the rules for swapping, and we alluded to this just a moment ago, are the following. We have to remember serial execution of a set of database transactions preserves database consistency. We can swap instructions on different transactions without affecting the result of any instruction. So for instructions operating on the same item, we can only swap reads. So if both transactions were doing something with account balance A, we can swap the blocks of instructions only if they're dealing with reads. If they're dealing with an update, we can swap them if they're dealing with updates on different objects. But as we mentioned a few moments, well, maybe a couple of slides ago, if they're both doing updates on the same object, we cannot swap them, because if we do, then we can run into a problem. So in this particular case, this is swappable. So we take a look at, no, this is not swappable. This is not a serial schedule. The one on the next slide is. So in this case, we cannot swap this set of instructions in T1 with this other set of instructions interleaved in T2. Why? Because they're both doing an update to the same item. They're writing to A and writing to A. So we cannot swap these two. On this and this, we can swap this one, this block here with this block here. So we get read B and write B, read A and write A. So we can move this up. So even though the first one we couldn't swap serially, we can swap these two serially. So we move this one up, and then this one could be moved down, and then in effect we have this serial schedule that we were looking at here. So it is equivalent to schedule 1, even though it's not a serial schedule, because it's transaction 1 and transaction 2 are running at the same time. But it could be made virtually into a serial schedule by swapping this first block in T1 with this second block in T2, moving this one up. If we could move this one up and move this one down, because they are not working on the same item, so we can swap them. They're not updating on the same item, so we can swap them. So even though this is not a serial schedule, it's equivalent to this schedule, schedule 1, which is a serial schedule. So let's look at these two. So can we swap things around here to make this into a virtual serial schedule? Obviously, this is not a serial schedule either. Parts of T1 are interleaved with executing parts of T2 if we were to run them concurrently. So can we turn these into a virtual serial schedule? Well, let's take a look. We're reading A and doing a computation on A. Well, here we're writing A. So we can't do a read of A and a write of A. Can't do that kind of operation on the same object. So we cannot swap these. Here we're writing A, and here we're writing A. So again, you can't do 2 writes on any instruction in this block, so we cannot swap these. So in this particular case, we cannot swap them and make them into a virtual schedule. So these are 2 transactions that the query optimizer or the database management system would not schedule to be run concurrently. It try and put them in with some other transactions that it's got in its queue. So here are those rules we were talking about, stated a little more formally. Intuitively, again, for instructions operating on the same item, we can only swap reads on both those items. For instructions operating on different items, we can swap reads and writes. But here's the formal set of rules, and they will not conflict if they're both doing reads on the same object. If they're doing a read and a write on the same object, they conflict. Same thing here. If they're both doing writes on the same object, they conflict. But if they're working on different objects, then we can swap them, and that's no problem. So if the optimizer can do the virtual swap, then it's equivalent to a serial schedule, and the sets of transactions can run together. And here's another example. So we can look at Schedule 3, and we can actually swap it around so that we make it the virtual equivalent of Schedule 6. So that means that it's conflict serializable, and we can run transaction 1 and transaction 2 together, even though they interleave. We can't swap read A, write A, read A, write A, because they're both writing to the same thing. However, we can swap read A, write A with read B, write B, because they're working on different objects. So we can swap these around, and then we'd move this one down. And then we've got this equivalent schedule that's serializable. Now, again, Schedule 3 is not a serial schedule, but we can virtually make it into a serial schedule like this by virtually swapping. We won't do that, or I'm sorry, the database management system won't do that, but the fact that it could do that means that this is equivalent to a serial schedule, even though it's not a serial schedule. And here's yet another example. In this case, we've got these operations that we see, and T3 and T4 are not conflict serializable. We cannot move read queue and write queue because we've got a modification on the same object. They're both working on the same object, and one of them is writing. Likewise, we can't swap write queue and write queue because they're both working on the same object. So these are not conflict serializable. The database management system would just have T4 left in the queue, and it'd try and find another one that it could run simultaneously with T3. Okay, let's go ahead and take a 10-minute break, and then we'll come back and start looking into indexing.